This tutorial will show how to integrate an MLG-2 ProNet for Ethernet IP using the RS Studio software. Additionally, a positioning application is solved using the central beam blocked function. The first step is to set an IP address for the MLG-2 either by using the SOPA software or by using the DHCP or Bootstrap protocol. In this tutorial, the SOPA software will be used to set a static IP address. Open the SOPA software. Once the device is found, drag and drop it into the new project on the left side of the screen. If there is no driver for the device installed, a message will pop up. Click on OK and then on the warning Install Device Driver in the device panel. Select Device Upload as the source for STD installation and click on OK. Once the installation is done, switch the device from offline to online by clicking on Offline in the device panel. Click on Read Parameters to synchronize the device with the project. Open the device and expand the item Ethernet IP from the menu on the right side. Select Static from the drop-down menu as the addressing mode. Set the desired IP address, click on Confirm and then on Yes to apply the changes. Start the RS Studio and create a new project. Select the PLC from the list and give a name to the project. Click on Next and then on Finish. First step in RS Studio is to install the matching EDS file for the SICK MLG-2. Click on Tools in the menu and then on EDS Hardware Installation Tool. This will take you to the wizard to install the necessary EDS file. Select Register an EDS file and click on Next. Browse for the relevant EDS file and click on Next until the installation is done. The next step is setting the path to the PLC, which is going to be programmed. Click on the RS-Who icon and expand the Ethernet node. This tree node will display the hardware connected to the network. Choose the PLC, click on the Set Project Path and close the window. Now we are ready to do the hardware configuration of the MLG-2. Right-click on the Ethernet bus item from the menu on the left side and select New Module. Enter SICK into the search field to filter the results and click on Create. Give a name to the device. The name must be unique in the network. Set the same IP address as previously assigned and click on Change to set the assembly connections. Look for the desired assemblies in the item 7.4 from the operating instruction of the MLG-2. The assembly determines the later available process data. Please note, the configuration of the MLG-2 will be overwritten by the PLC if you choose an assembly which contains configuration data. If you wish to keep the configurations you did in SOPAs or via the web server, select the assemblies without configuration. In this example, the normal assembly with configuration is chosen and the current settings will be overwritten. Confirm the connections by clicking on OK. Now the MLG-2 is integrated in the Ethernet node. Click on this icon from the controller and select Download. In the pop-up window, click on Download again. Answer Yes to change the controller mode to Remote Run. The status icon changes to green to indicate that the controller is in run mode. Double-click on controller tags from the tree menu. The variables from the MLG-2 are displayed in the main window. In the variables, C stands for configuration and I stands for input data. Expand the I node and then the data subnode. The list shows the data as packages of 1 byte, signed integer. The application example that is solved in this tutorial is positioning the center of an object in the center of the light grid. This requires the function CBB, which is central beam blocked. All basic functions in the assembly are unsigned integers 16 with 2 bytes of width. When the light grid is interrupted, their value change. CBB, the central beam blocked function, is in the place number 9. 9 times 2 is 18, so the CBB information following is in bytes 17 and 18. Since the list starts with 0, we need to look for byte number 16 and 17 for the CBB information. To solve the positioning task of this example with best accuracy, we use the option High Measurement Accuracy. Go back offline and navigate to the configuration node to set the device in high measurement accuracy. The following information is retrieved from the item 7.4.3 in the operating instructions. The byte 1 defines the performance options. The high measurement accuracy performance is attributed to the value 1. In the performance options field, set the value to 1. The device will be switched to high measurement accuracy mode as soon as the new configuration is downloaded. Do the same download procedure as above. If the project is online after the download procedure, go back offline. Now we are going to use the CBB value in our program. As the first step, we need to create a variable of 2 byte width for the CBB data. Navigate to the controller tags and choose the tag Edit Tags. Create a variable which is called CBB in this example. Assign the data type integer. In this example, we will use structured text as programming language. To do so, right-click on Main Program from the Tree menu and select Add New Routine. From the New Routine window, select Type Structured Text. Name the routine, for example, as st_routine. If you don't need the by default created letter routine, right-click on the routine called Main Routine from the Tree menu and select Delete. Confirm the deletion of the main routine with Yes. Right-click on Main Program and select Properties. In the Configuration tab, assign the st_routine as the main routine and click on Accept. Double-click on the st_routine to access it. Type in cop for the copy instruction. First argument of the copy instruction is the data source. Expand the inode and then the data node and find byte 16 in the list. Hit Enter to confirm and add the destination variable called CBB. The last argument is the length, 2 bytes. Save it by clicking on the floppy disk icon. Download by clicking on this icon. Confirm the download in the pop-up window. Once the download is done, confirm the remote run mode with Yes. Select Controller Tags in the Tree menu to check the displayed variables. The CBB variable has a decimal value of -1. In an application where an object shall be centered, the CBB value changes as soon as the object center matches the defined central beam of the MLG-2. -1 shows that there are no beams blocked at the moment. This changes as soon as the object is present. Thank you for watching this tutorial and hope to see you next time.